Thank you to be here for the lecture of today. Today, I would like sum up um, what I told you about the sliding mode control. As I told you, was in a selection again of a very large topic, sliding mode control. I would like to sum up with one example, an introductional example, and then I will uh, tell you about another example, which in any case can be considered for your future, probably, if you want to do, for instance, thesis with me. It is possible. Huh? This is enough to ask some administrative aspects to sign an agreement. Uh, because we are here in my lab, I am in the lab today, as almost always, because of when I have this meeting at the university, I'm in another round, not totally far away from my lab. We have three segues. I don't know if you know this system here, but I will tell you during this lecture here. Now, in accordance with this method, extremely important in robotics, basically this segue is in a robot system, not to move, no? But I will tell you later. Based on inverse pendulum principle or system. It's a very important method, the sliding mode control, for different reasons, in particular based on this Lyapunov approach. It could be that some of you already attended the classes in lab. I had the classes in the lab. Of course, in this case, it's a little bit boring. But in any case, it's important eventually also to repeat. But I took just a part. I will take just a part of this lecture. But I would like to emphasize what we did in this course, and in particular, the first theorem of Lyapunov. We have seen the second one, and we can see now the connection between considering an example, introductional example, to an important robot system, even though the robot system is a segue, I will not consider in detail, I will consider just the pendulum, because really this is, in any lecture, in particular in Zoom, extremely heavy. But we worked a lot here in my lab with control, also with experimental measurements. We have three segues. I don't know if it's clear what is in a segue. Let me show you in a picture in order to understand that if you are interested to work in this system, or it could be that you have also in your lab. Let me show you in a nice picture of the system here. Let me see. Segway picture. Yeah, I share now. Huh? One second. Huh? Oh, yeah. We have a problem to log in. Let me. Oh, no. Let me take another example. Here. Let me see if this is visible. Yeah, probably you know this. Of course, this is a little bit more advanced, but probably you have also in Huch. Here in Lüneburg, we have I think I have seen in Huch when I was there. But in any case, it's clear what I intend. At the beginning, this robot, this moving isn't a robot in this sense, was used by the policeman. I don't know if you can remember this. Today is used everywhere for every people can put a coin or €1. You can travel. No? I will sketch at the end of this lecture a little bit what we can do, what we do also in my lab with the sliding mode control, this Lyapunov approach, but starting just for the pendulum. No? So we complete with an example, a practical example, but again, to analyze this kind of system, to analyze this kind of system, this is in the project, or can be included in a PhD program, no? Because it's really complex system. Of course, complex or complexity, what is the meaning of complex or complexity? Depends what we want to analyze. Complexity is like abstract concept, which depends what is our goal. Uh, Also, the short equation could be extremely complex depending how we want to go in depth. Complex or many equations could be also an easy, could in a complex system of equations could be also formulated an easy problem. It depends in the sense. Okay, let me start. I hope that not many students already heard this lecture from the course of lab, but in any case, I will try to emphasize aspects related to our course. Let me switch on the lateral camera. About the material in the WeCamp, we will consider later. No? I think you can see now the slide. Let me fix up a little bit the focus. Uh, ah, 1 second. Uh, second, because yeah, I remember it was very nice for different reasons when I held held the lecture in Uch. First of all, because I like very much your university. Secondly, I like very much your town because it's very international town, multicultural town. Once I went also with my wife, Ellen. I told you that for one side, Ellen, my wife, is half Polish. Raczynski. Raczynski is a classical, classical Polish name. I remember we had a good time really, even though the course was, how possible to say, concentrated. Basically, I was 10 hours out from the hotel, and the evening I had to prepare the lecture for the day after. And this means but anyway, we remained during the weekend, and nevertheless, we enjoyed the town together. Anyway, let me start. 1 second. I don't find the stuff which I had here. 1 second, where is, okay, this I need. It could be that I need through this one. Oh, let me start now. Look at this picture here. Um, It's a picture of a system which you know from probably other courses in physics, in technical mechanics, or general mechanics. It could be that you have seen this pendulum is a classical representation of the pendulum. Of course, in the same way, which is our possible goal for the project, we have a pendulum which is not exactly in this position, but this is just a reference problem. If you think about the Segway, uh, we have something like that in which uh, the angle to be controlled is this here. No? Theta, I think, is the name. Let me see, because I cannot see well. Alpha, excuse me. But this is just a possible representation. I mean, we will see also today with the simulation that if the reference is this one, I can consider this position here just thinking to control the system here, we will do together. At the position pi, the position pi is this way, pi. Also, of course, for this system here, it's zero, depends. Let me say, for this system here, if you represent the system this way here, this vertical position, let me say roughly speaking, so we can understand better, with respect to this reference here is pi. This means we can control the system, the pendulum, at pi, in order to go in the graphical representation of an Segway, of course, we control, if this is the reference, the system at zero. The possible scheme of the Segway is this one, these robots. No? I I push, let me see. I push ahead and I will travel. I will explain the system here. Of course, this could be a project, and a thesis, could be in a program also in master, but also in PhD, also with different aspect of this robot here. Of course, here the representation is in two-dimension, let me say, structure. Of course, we have a scene in the picture something like that, in which we have. Do you remember? We have the possibility to move the arm here not only in this angular here, but also is a tilt angular. No? Anyway, um, yeah. But let me go ahead. Yeah, let me consider this reference here. This reference here. Of course, here is zero. This angular L alpha zero means in the, let me say, roughly speaking, the low position, lowest position. Alpha pi is the vertical position. Let me say in the higher position. No, this makes sense also. We have this point is fixed. We have a mass m. We have a length which is typically is fixed, typically, but of course it would be interesting in the PhD program to consider also how I can control the system, same way if I can also consider a difference length. Therefore, I told you that this kind of problem is an extremely complex problem. If you consider also the problem of the actuation here, which kind of actuator, the dynamic of this actuator, the system is extremely complex. Also here, in this representation, we have a torque acting around this point here. Let me formulate in this form here. This means here we have an actuator. Typically, it's an electrical actuator. We generate a torque. We generate it. It's not the case of the same way. No? I will tell you a little bit. We don't have here in this joint here of this robot here an electrical actuator. I will clarify how we'll move. I will clarify how we will move if we are driving based on Lyapunov from this sliding aspect. Here, nevertheless, to move, to control this kind of system, which is not exactly the same way, I can say it's a part of it, but it's also not correct. Because here, in order to move, in order to control this position, I need an actuation here. I need an actuator. Typically, it's an electrical actuator with its dynamics, with its model. About the model I told you at the beginning of the semester. Here, no, we don't have here in this joint. We don't have it. This joint, in the same way, is not actuated. Also, this one. We will see how I will move. The movement is in a reaction. That's interesting. Assuming that I have an actuator, but I don't consider the model of the actuator, because if I consider the model of the actuator, also the system is extremely, I don't want to extremely complex, but more complex. I would like to say extremely complex to explain in a part of the lecture in any case. T of t, torque, is our input. But of course, practically here, in this lab, we have a T of t generated by an actuator, an electrical actuator. This means the input typically is voltage. I have to feed the actuator with voltage. The voltage came, do you remember, from a controller, and then I will move everywhere. I can do some tasks. But in particular, the idea is to control the position, I don't know, a pi divided 2, see here, at pi, and so on. T of t, in our case, is our input. This means it's the output of our controller. In this sense, the controller includes somehow the actuator. It's just to understand, G is the gravitational force, B is the friction coefficient. About that, I told you a lot. I will come back on this point and this topic here because it's extremely important, the application in robots. In automation, this friction coefficient or the friction model or the mechanical losses are extremely important is in the field. As I told you, I am not expert in tribology, the fields of the mechanical losses. The name is tribology. Let me write for you the word. This is really alone is in the field because it's extremely complex to model the friction, the losses, the mechanical losses. And this topic here includes also lubrifications, the theory of the lubrification. I am not expert. I mean, I am control guy, no? Control robotics guy. I am not expert or in depth of this. Uh, but of course, in control, we have to a little bit manage such kind of models because we have many models. The easiest one, as I told you until now, is the model, the linear model. But I will repeat also today a little bit about the Coulomb model, which I already told you. But of course, we have a Lou-Gray model. We have many other models in order to adapt the model at different systems and different working conditions or the working points. Mg is the gravitational force, the product between the mass and the gravitational acceleration. Look here for some details. We are not here to analyze in depth the model because probably you know already. J is the inertia, which is in this ideal situation is m multiplied the length square in this ideal situation. Length, L is the length of the arm. No? Do you remember my boring concept concerning the states? Here, basically, we have in the system here two states, angular position and angular velocity, because basically we can localize, let me see, or we can represent the internal energy, let me say so, in terms of potential energy, in terms of kinetic energy. Probably you heard about that. I don't want to insist on this, but it's in one example, I think I showed you in the aerostat system. Do you remember mg multiply the level? No? Yeah, exactly the level. You are better than me in math, I am sure, in mathematics. L multiply sine of this somehow represents this distance, no? If I remember well. This means this distance here reflects the potential energy because when this distance is zero, we have this point here. Basically, is the do you remember lowest point in this sense? Potentially, in sense of potential, we don't have. We have energy zero with respect to this angular position. The kinetic energy is related to the velocity. Anyway, I told you about this. It's not exactly now to repeat. Very important to repeat that you have two states or two state variables: position, angular position, and angular velocity. Let me see. I forgot to say something. Yeah, the orientation. But this is already known from physics, from technical mechanics. I have to consider a positive direction of the position, this one, which is also the positive direction, the velocity, angular, no? Velocity, angular position. And yeah, in this sense, typically, but not necessary, but easy for the representation, we consider also in the same direction also the inputs, in this case, the torque, positive, let me say, anti-clockwise. We have to choose, we have to orient in the sense of how possible to say, do you remember I told you about two possible concepts in terms of orientation. Here is the positive, let me say, direction and forces of torques, with respect to the negative. Um, and another concept of the orientation is the orientation in terms of system theory, which is the input, which is the output. Here, what I intend is the orientation of the movement. Positive anti-clockwise for the input, positive anti-clockwise for the torque, positive anti-clockwise for the states, alpha and alpha dot. Here, why mg is down. Okay, this we can justify also intuitively, in the sense we can imagine that the representation, or the graph, represents the real situation in which the gravitational force is the direction is down. This means, let me say, we don't need to think about, but if you want, we put this positive direction with positive direction of the input torque. This direction generates in a moment, or in a torque, a moment equals torque, in against this positive direction. We will see, we will consider the minus in the sense in the balance, in the Newton balance. But I think could be clarified a little bit better, but I don't have time because probably you know better than me how we can organize directions, positive and negative orientation in sense of motion of such kind of system. Again, very important to repeat, alpha and alpha dot are the state variable and they are connected with the internal energy. Now we have two energies, potential and kinetic energy. Look now at balance. We can see now what I told you until now. Again, m multiplied L square is j. Don't care about the model at this moment because we are more oriented in control. But of course, we have seen that the modern or the selected control strategies are model-based. This means, nevertheless, we have to take into consideration a model which can be done from literature. Again, we cannot be expert on everything or everything. Of course, we have to be knowledge about everything, but of course, we can read books, literature. Otherwise, why we have books? What is the reason to write papers or to write books? This one, because we can already have a support for our control, in our case, for knowledge that we are not the expert, but of course, about the structure of possible equations, about the structure of possible model, we have to have an ideas about. You remember the inertia from high school, the inertia, multiply the acceleration, in this case is the angular acceleration, this is basically is the Newton balance, in terms of torque, equals the input torque minus the friction torque, which is linear in our representation. But I will tell you a little bit two things about, again, about the Coulomb, because important also. We can see that in accordance with this model, is proportional to the velocity. We have also more complex model, just depending on the velocity, but also depending on different variable. Again, this friction model is extremely complicated field. Why not? Minus, you remember I told you that this force here generates a torque on a moment, which is against the motor torque if this is the positive direction. Also, this is minus this for, let me say, because in the losses. No? Because in the losses. About that, I can improve also the answer, but let me go ahead because otherwise we don't have time to analyze the control. MGL sign is the last elements which we have in this torque balance, which basically is an energetic balance. The dimension of the torque is energy. We can say that this is not enough force balance. We can say better to say torque balance, but the torque is energy in this sense. Be positive. State variable I already told you, which reflects potential energy and kinetic one. I don't need to clarify uh, these two sentences because I already told you many times. Look now at the version of the model in terms of, let me say, variation of states variable, variation of state variables. This control forms. Look, alpha, our state variable, equal alpha 1. I call position. I call this position. Alpha 1 derivative, I call alpha 2, I call velocity. This means alpha 1 is the position, alpha 2 is the velocity. It's just a position. I already told you last time, to have more flexibility in the nomenclature. We can work also with alpha, alpha dot, and alpha dot dot. Basically, this trick here is there in order, don't use many dots, and in order to, in an explicit form, to have the position, the velocity, to have the position, the velocity. Alpha 1 is the position. I don't need to do a derivative of alpha 1 if I use alpha 2 because I already defined that alpha 1 dot is alpha 2. Meaning, it seems to be a little bit strange what I told you, but now we can see here the nomenclature advantage, but just the nomenclature advantage. Here, no, I didn't introduce any new concepts, just positions. Look here, in accordance to this equation and this equation here, I mean, alpha 1 is the position, the derivative of alpha 1 is alpha 2, is written here. This means the variation of the position equal the velocity, equal velocity. This sentence I don't need to comment. Alpha 2 derivative, this means the acceleration, angular acceleration. I don't tell you anymore about angular. No, everything is angular. Angular acceleration, angular velocity. Alpha 2 dot equal this equation here. Alpha 2 dot means alpha dot dot, because this is the acceleration with respect to the nomenclature alpha. This means I will divide everything by j, which here I put in terms of ml squared because I noticed that here I can simplify m and L with L squared in the denominator, and I will obtain this. It's in a typical form because we can do many consideration about the period of the oscillation, but at this moment is not the topic to analyze the dynamics of this, but the control. But also, in any case, the model is extremely important. Look here. This is the input divided my inertia, ml squared, minus b divided by inertia. Look, instead of alpha 1 dot, this is I put explicitly, typically we write alpha 2. The idea is to use on the right part of both equations, alpha 1 and alpha 2. Here we don't need an alpha 1, but here we can replace alpha 1 dot in terms of alpha 2, and here we have alpha 1. No? This we can distinguish clearly when we have the position, the contribution of the position, and the contribution of the velocity. And this allows also, do you remember I told you to build in case of linear system, to build using matrices, this particular expression or representation of the model. Concept. First theorem of Lyapunov. I didn't tell you about the first theorem of Lyapunov. This is a new thing which I would like to consider today. Please pay attention. I will ask in the project for the examination, calculate, this is the question, and we will see today, the equilibrium points of a system, or in the project, in the examination, I will put directly the equations, because otherwise it's too much to build the model. I will put directly the equation in accordance that we know we are able to build the model. The reason is we didn't do, I mean, the course is not on modeling is control. This means it doesn't make sense to ask about, it makes sense. It could make sense, but we did a few things about the model. We did nevertheless something because to control, uh, mm, let me say in the modern way, we need, or let me say, selective control systems or selective control strategies are basically model based. Okay, let me see the definition. Autonomous system. Easy to remember because autonomous means could mean without input. No, I go autonomously. This means I don't need any guide. No, 1 second because probably no. I hope that you see the lecture, no, the manuscript. Uh, I go autonomy in my life. Let me say so. It means probably I don't need any guide. Anyway, this is the idea. Input zero. Autonomous system. The idea is to calculate for this autonomous system or in a natural way, and let me clarify the concept using this wording, where the system remains in equilibrium. This is the definition, the mathematical definition. I sketched, of course, the mathematical definition, a little bit more complex, but let me go ahead intuitively. Look at this. The definition says that for each t, the derivative of alpha 1 is equal to 0, the derivative of alpha 2 is equal to 0, meaning, in accordance with what I told you until now, that the states represent or reflect, probably better to say, the state represent or reflect the energy. This means in the point in which we don't have changes of energy. For each t, all the time. Exactly as I commented here. Look, if alpha 1 dot is equal to 0, please replace this in the first equation, for instance. Easy, extremely easy. If I put here 0, I have automatically that I find velocity 0. If I put here 0, I have velocity 0. This means it's necessary to have the velocity 0. This makes, in general, makes fully sense because if the velocity is not 0, we have the kinetic energy. This means it's trivial to think that it's reasonable to think to intuitively to validate that the definition reflects, let me say, the common sense, reflect also what we observe in the lab. Again, I would like to justify this sentence here. Why I'm saying that the definition reflects, the definition makes sense, because mathematically, let me show you this concept here, because it's extremely important philosophically. Mathematically, we can define whatever we want. But of course, in engineering field, in physics, the definition should somehow reflect what we want to describe, should somehow don't generate contradictions with experimental results, also with the evidence, what we seen, even though on the second sentence we have to be careful. But in general, for the engineer, in engineering fields, of course, we can define what I want. But the problem is how useful is this definition. This is a little bit, but don't want to go in depth on this because it's a little bit more philosophical, but you understand what I intend. In this case, in this specific case, if you consider this pendulum, and I say the position, the excuse me, the variation of the position 0 implies that the velocity 0 makes sense. Totally. In general, this makes sense. And this means this sentence here can be, at least in this example here, very well, let me say, validated. Validated means that the definition reflects our common sense. Look at this now. From this condition here, together with this, because this is already the condition which I need. I mean, calculated by or using the definition. Look here. This is zero by original definition because I would like to look the natural equilibrium point. Natural means without solicitation, without input. Without means T of t equals zero, no? In this case. This is zero. This is zero from the first condition. But this is actually the velocity is zero for each t. Yeah, I did input because if this is zero for each t, the resulting alpha 2 of t equals 0 is also for each t. Let me write. Because this came from the derivative alpha 1 equals 0 for each t. This means also for each t. But this is 0 for each t. If the velocity is 0 for each t, also the acceleration is 0 for each t. Clear. Because it's the derivative of 0 at any time. This means 0, 0, 0. This means this is the condition which can be written in this form here, 0 equal sine of alpha 1t. Now, sine of alpha 1t means mathematically alpha 1 k multiply pi for k starting from 0, 1, 2, 3, 4, theoretically also minus 1, minus 2. Mathematically, we have infinite points. But of course, practically, we have just 2 points. K equals 0 and k equal 1. Why that? Because the rest of the point, they are periodic. Look, we have basically this equilibrium point characterized by k equals 0 mathematically. This means position 0, velocity 0. Velocity must be necessarily 0 for each t, no? For each time. No? And this position here, this means k equal 1, even though I didn't write. Let me write if you want. Yeah. Let me say the lowest, just roughly speaking, position, the highest, roughly speaking, position. 2 equilibrium points. But of course, we can intuitively think that we have a difference between which one. If I move a little bit this one, I will come back on the equilibrium point. If I move a little bit from this equilibrium point, again, alpha 1 pi, alpha 2 pi, I go far away, I will end up in this. Now is the second argument of today to analyze or to characterize the equilibrium points. Look at this remark in red. This remark allows me to justify why it is important, nevertheless, this analysis. The analysis of to calculate the equilibrium points and to classify. I didn't classify again. I didn't classify until now, but I told you that it is necessary to classify. It's necessary to classify because we have a big difference between, let me say practically, to control the system at this position and to control the system at this position. It's clear. Yes. Of course, it's a little bit, let me say, I don't want to say more difficult, but yeah, I can say roughly speaking more difficult, not because here I need a control. I need a control. Here it could be that I don't need, depends on what is my specification, because this point here is, again, if I have a disturbance which moves this position here, and the disturbance, assuming that the disturbance is limited in time, also in amplitude too, of course, I will come back somewhen on this position here. Here, I'll never come back. Let me go ahead to classify the points, the equilibrium points, but let me tell you about this. Why this remark? This remark is there because controlling the system is very important to analyze how far away is my working point, this case pi divided 2, with respect to the equilibrium points. Because of course we can understand that to control the system at this point here, which is not an equilibrium point, It's more difficult than to control, in any case, the system at this point, but also more difficult than to control the system at this point here, because this is not an equilibrium point at all, at all. It's really the far awayest point with respect to this and to respect to this. To control in some other points could be, I would like to say, in general, uh, easier than to control the system here. Why that? Because here we have the maximum uh, torque generated by the gravitational force. This means here, really, we have to energetically spend energy. Let me go ahead with the classification, and then I will repeat the theorem which we have seen last time. This means the second Lyapunov theorem. We will conclude with the control, and I will show you the simulation. Uh, of course, I will upload everything. Look here. Theorem 1. Until now, I didn't tell you about the theorem 1 because we have seen last time the theorem 2. I don't remember if I called theorem 2, but in any case, it's exactly the theorem which we have seen last time. This is another theorem which allows to classify the equilibrium points. It's important to classify the equilibrium point because, as I told you, the nature of this equilibrium point is totally different with respect to this one. Yeah, let me say, roughly speaking, is more easier if the specification is not so exigent, is not so strong. Because if I'm not interested to the time, if I have a disturbance here, somewhere I will come back to this. If the goal is must be somewhere in the bar and this point here, I don't have to do anything. Here is the situation much different. Let me see here. I have a dynamical systems. I have a dynamical system, just one, Susan. This is the general form which I already told you. X is in a vector, the derivative of the vector is equal f. Why now I am writing about, I am considering f and not the matrix A, B, C, D, as I told you. In this case, it's just the matrix A and B is involved in this representation because you remember in linear system we have x dot equals A multiply x plus B multiply u. Here we see that everything is in the function, not specified of x and u, right? Um, because the system is non-linear. This means if the system is non-linear, yeah, we cannot use directly, or at least not so directly as I told you last time, in the first part of the course, with matrix A and B to represent the variation of the states. Then, in the vicinity, in the neighborhood, close vicinity of the equilibrium point, x0, one equilibrium point, we say that the system is asymptotically stable if, let me go ahead to this, all real parts of the eigenvalues of its Jacobian matrix J. This means we need to build the Jacobian matrix, calculated at x0, the Jacobian matrix is calculated at x0, are strictly negative. Probably you remember this, no? The eigenvalues, which represents the answer of the system, of the free answer of the system. In this case, it makes sense to speak about free answer because the input is equal to 0. But in general, you remember that the exponential elements of the exponential function characterizes the stability. I mean, if it's negative, the real part, the answer is going to 0. I already told you at the beginning of the semester. If it is enough to have one real part of the eigenvalues positive, and the answer is going to infinite. This means if considering this basically Taylor approximation, because the Jacobian matrix, I don't know if you remember, I will tell you about as an possible repetition, represent the matrix of the first derivative, partial derivative, which I will show you in 1 second. And this means reflects the Taylor approximation. This means if the Taylor approximation in this theory, I don't have time to do the demonstration, but intuitively we can guess that is related to the Taylor approximation. If the eigenvalue which represent the dynamics of the system in neighborhood close to the system, because the Taylor, I don't know if you remember in math, represent how possible to say the derivative around the point x0. The derivative is always in a local, very important keyword, in a local concept. I don't know if you remember in gymnasium, in high school too. Secondly, the system is unstable if just one, as I told you until now, I already told you about that. Is enough one real part positive, because if you remember the exponential, the eigenvalue of a matrix, I told you also in the first part of the course, represents the exponential element of the exponential function. The exponent, let me say, element of an exponential function. If it's enough one to have with real part positive to say that around this point or locally, look at this word, extremely important in nonlinear system. Locally, the system is unstable. Locally, in our sense, means in the sense of I mean, its approximation is unstable, and then we say the approximation is local valid. No? The nonlinear system is locally unstable. I don't know if it's clear what I am doing. I am approximating the system. We use the Taylor, basically, and this can give us information about the original system, which is nonlinear, just locally, because the idea is to use the Taylor, which is a local representation based on the derivative. If we have also just one, or at least one part, real part, 0, we cannot conclude anything. Anyway, the demonstration a little bit articulated. You can find some books, but I don't have time to attack this demonstration. Let me tell you again about the second theorem, and then we will proceed directly using the first theorem to classify the 2 points which practically we found. And with using the second theorem, we do the exercise which we did last time for another system, basically to build, to design, better to say, the control system for 1 or 2 points, but also using the MATLAB, no? Because this could be also a possible question in the exam. No? Second theorem, we know. We have a system. I don't spend words about this. We have, in this case, an equilibrium point, or we want to attain a desired equilibrium point. Why that? Here. You remember, I want to control here. This means I have an equilibrium point. I want to control here. I have another equilibrium point with different nature. Now we will classify together. It's intuitive to say, to demonstrate, also it's easy, that this equilibrium point is asymptotically stable. This equilibrium point is unstable. It's easy intuitively. We will see mathematically in accordance with the theorem 1. Unstable because if I move a little bit, I will fall down here, no? And here I will come back here if I move a little bit. We will go in depth later. But anyway, I can control here, I can control here, but I can control in every point of the working space of this system, a robot if you want. We will see shortly when we speak about the Segway, we are speaking about the robot. The example is here. I can control also here. My equilibrium point, which I want to attain using a controller, could be also this one. This is not a natural, let me say natural, or an autonomous equilibrium point. But with the controller, introducing a t different of 0, we have seen also last time, and a t which came from a controller, I can realize an equilibrium point theoretically wherever I want. Also here, also here. We will see also with MATLAB. It's extremely easy once we have the control law which came from the second theorem, which you already know, to change the point in which I want to control the system. We will see with MATLAB. Anyway, you remember to summarize everything. You remember this? An Lyapunov function candidate, v of x positive, in around an equilibrium point could be a natural equilibrium point, but could be any kind of equilibrium point, could be also a trajectory. We can see here, x0 of t, whatever I want, theoretically, at the equilibrium point or along the trajectory must be zero, an equilibrium point, or in a point, it doesn't matter which one, in a point which I want as a possible equilibrium point, a desired equilibrium point, not necessarily the natural equilibrium point, or trajectory, zero. We will coming back on the application, but we have seen 2 or 3 times in this lecture. The derivative at this x0 equilibrium point or desired point or desired trajectory must be negative. The derivative, this means with respect to the time. And at this x0, exactly at this x0, the derivative must be zero. Let me see if I have to. Yeah, in this sense, I have to correct. Excuse me. Is around, it's not wrong. It's a little bit, you have to clarify better. Around, in the surrounding of x0 negative, at the point must be zero. I do remember I told you better last time, but it's correct. I don't want to change anything, but I have to explain. I have to explain. Negative in surrounding the derivative with respect to the time in the surrounding. This means this notation. I simplified a little bit in the theorem. There are more words not to clarify, but it's clear. No? In a domain around, at the point must be zero. It is easy to implement that to explain. Okay, let me see now what happens. Page number 4. Number 4. Let me go ahead 15 minutes and then we will take a rest a little bit. So we will see mathematically the application of the theorem 1. The equilibrium points are these two, characterized by alpha 1 equals 0, alpha 2 equals 0, alpha 1 equal pi, alpha 2 again equals 0. No velocities, otherwise, you remember I explained, we don't have the kinetic energy is 0. And you have 2 possible positions. Anyway, first equilibrium point, second equilibrium point. Now, I have to calculate the Jacobian at equilibrium point 1 and equilibrium point 2 to classify the first equilibrium point and then the second one. Jacobian. Do you remember t or the u in the classical notation u, the input 0? This means I don't put here. No? But to be precise, I have to write comma 0, but sometimes you find also this definition. In our case, we have two state variable, alpha 1 and alpha 2, which here I called x1 and x2. But just because here is the general expression of the Jacobian. For two variables in books, you can find x1 and x2, but x1 in our case is alpha 1, x2 in our case is alpha 2. Of course, in the first equation, we have just a function of alpha 2. Do you remember? Alpha 1 dot equal alpha 2. But anyway, this is the total general definition. The Jacobian is the matrix of the partial derivative, which we have here the derivative of this f1 with respect to x1. This means with respect to f1, alpha 1. Here is the derivative again of f1 with respect to x2. And the second line, excuse me, the derivative of f1 with respect to x2. The second line is the derivative of f2, this part of the field. I don't know if this word, field is this vector characterized by this component and this component. I will come back on this. The derivative of f2 with respect to x1, the derivative of f2 with respect to x2. Let me apply it at our system. Our system is this one, t equals 0. Why this is the Jacobian of this system here? Why it is 0 here? Because it's f1, this expression, derivative with respect to alpha 1. Again, here is not the derivative with respect to the time. It's the partial matrix of the derivative because we approximate in the space domain, not in time. No sense approximating. I mean, not in this sense. 0 because the derivative of alpha 2 with respect to alpha 1 is 0. Why is 1? Because it's the derivative of f, this expression here, which is alpha 2 with respect to alpha 2. This is 1. The derivative of f1, which is alpha 2 with respect to alpha 1 is 0. The derivative of f1, which is alpha 2 with respect to alpha 2 is 1. If I apply this definition here, let me say to this second equation, or let me say the second component of the field consists of the field of this system consists of two components, is a vector of two functions, alpha 2, and this expression as in the second component. Now, why this here? Because it's this f2 with respect to alpha 1. But we know, with respect to alpha 1, that is 0. This expression, derivative with respect to alpha 1, you know that the derivative of sine of x with respect to x is cosine of x. This means minus GL remains, and I have instead of sine, cosine, with respect to alpha 1. Why the derivative of this expression with respect to alpha 2, which is this one, is this here? Because this derivative of this element is 0, and this is a linear function with respect to alpha 2. Therefore, I have this. Then, of course, I have to calculate this for these 2 points characterized by alpha 1 equals 0, alpha 2 equals 0, and for the second point, alpha 1 equal pi, alpha 2 equals 0. This means I can, before, if you want, calculate the matrices at this point, calculate the characteristic polynomial. I don't know if you remember from math, to calculate the eigenvalues. You remember the theorem is related to the eigenvalue of this matrix here. I can calculate the eigenvalues. The eigenvalues, I don't know if you remember, can be calculated by this expression here, which is lambda I is the identity matrix, in this case 2 times 2, in order to obtain directly this algebraic expression. This means this is the matrix alpha, excuse me, lambda 0, 0, lambda, minus this expression here, we have lambda minus 1. We have this element here, but plus. Why that? Because we have a minus j. And then we have lambda plus this element here, because again, minus j realize this instead of transforms this minus beta in plus beta. Lambda minus beta divided ml squared. Again, this expression here came from this expression because it's lambda, the matrix lambda 0, 0 lambda minus this expression here. Try to do at home. This is easy to see. If you want, I can write here. This is lambda I. I is a suitable matrix 2 times 2 in order to realize this algebraic condition. Condition means to do the difference. This matrix minus this matrix is a minus, no? Yes, also a minus. This matrix, this matrix minus this matrix is easy to see is this matrix here. Determinant of this, and remember, this multiply this minus this multiply this is this one. Now, I calculate at the equilibrium point this characteristic polynomial. Of course, I can directly calculate the matrix at the equilibrium point starting from here, but it doesn't matter how, when you do. We have this expression. And if you remember the Cartesian theorem, but if you don't remember, you can calculate lambda 1 and lambda 2, we can realize easily that both lambda are negative, strictly negative. This means definitively we can say that the point characterized by alpha 1 equals 0, alpha 2 equals 0 is an equilibrium point asymptotically stable. It's intuitive. No, it was intuitive. If asymptotically stable means if I move in this around, let me explain how possible to say intuitively. If I move in the surrounding of 0, I will come back to 0. Of course, in infinite time. Remember this concept in infinite time because, of course, the dynamics is characterized by exponential function in terms of the approximations. Practically, no. We see that we stop. But about that, I already told you. About that, I already told you. This depends of the model. Now, I didn't consider the static friction. This means we cannot say mathematically that infinite time I reach 0. I will reach 0 in infinite time. Therefore, the word asymptotically stable, because I am considering the eigenvalues of this structure. Let me conclude. What happens at pi 0? I will calculate the polynomial characteristic at pi 0. I will have this equation here. This, in accordance with the Cartesian theorem, we have an eigenvalue with real part positive, an eigenvalue that real part positive, unstable. Unstable means that I will go far away from the equilibrium point. In this case, means I will end up in the other equilibrium point. Okay. Before starting this, I think we can stop, but I need 5 minutes to tell you about one particular remark, and then we will apply again, as last time, the second theorem, in order to control the system, for instance, here, and then with MATLAB, but also here mathematically, we will control at pi divided 2, no? Remember, horizontally. But this is interesting because the same way, we will see is controlled at this position here. Let me see, because before, I would like to start this part here because we already know the sliding is basically is the most important part because it's the constructive part, even though to analyze the equilibrium points is extremely important because we have a feeling how difficult it is to control the system in this point. Sometimes it could be useful if you have the possibility to choose for some different reasons, the equilibrium point could be useful to choose the most convenient energetically, assuming that the most convenient realize nevertheless the tool, the goal. One thing, let me see. Yeah, the last things, then you take a rest a little bit. Until now, we have seen, I already told you about that, but I will really 1 minute to repeat. We are considering the friction force, FD, FA, FF, FR, just consider this linear part. But you remember, I told you, and the possible, not the unique one, not the unique one, representation, more realistic of the friction. This is the model, is the Coulomb friction. Is, you remember, something like that. But also we can consider also higher order of the polynomial. Very important. Everything is important. Depends of the nature of the friction. Depends of the many things which I don't know also. No? Typically, when we're working on this topic here, we have something which can help us to build the model, or we try to, in the literature to find a possible model which can reflect our situation, basically in the fields of modeling and friction modeling. There is a literature, no, in this sense. Very important, this one. This one is responsible for achieving this asymptotically stable equilibrium point, which mathematically, at least just considering the linear part, is an equilibrium point, let me say, in infinite time. But using this element here, I told you already many times, we can also see a little bit more clearly to understand better or to simulate exactly that I will achieve the goal in finite time. The reason is, and remember, I told you, let me forget this um, component here at this moment. Of course, if the resulting force remain between d0 and minus d0, the amplitude of this static friction, I will not move. We can see x derivative, which is the velocity, remain at 0 here. This means we need a force to overcome to move, but also if I am moving, when the force is in the interval, I will stop. No velocity. No velocity means the velocity is 0. No? It's clear a little bit to understand. Very important to repeat again, SGN, which is this function here, which characterize the even part of the function, x dot square. Also, this is even, no? A constant even. Why that? Because the friction is an odd function. Here, I don't need to put SGN. Is an error if I put multiply SGN, because I will transform an odd function an even one. The model of the friction is even because it's always against the movement. In the Newton balance, here, abstractly I put so, but in the Newton balance, you remember it's minus. No? Input force, here we have a torque in our case, but yeah, you put the force. You can write here torque, no? T of D, T of D, T of D, torque. Is always against the movement. This means again this minus what we have here, no? As a function of the velocity. The velocity characterizes the movement. But this, I already told you many times about that, no? Just to repeat it. Just to repeat, it's nothing new. Of course, in our case, x dot is alpha 2, alpha 2, alpha 2, alpha 2, alpha 2, in particular square here. In our case, f is not f, is not t. TF, I don't remember. Probably I didn't call. Anyway, it's clear what I intend. At this moment, we are considering just the linear part. If you simulate just with the linear part, we see this infinite time convergence. But if you include the model this, you can see that we achieve the goal in finite time. The reason is when the force, the resulting force, everything which we have in the Newton balance, or better to say, the resulting torque in our case, remain here or end up here, we stop directly with the velocity zero. This means we achieve the goal somewhere uh, in the braking phase, let me say. Of course, let me say here, in the starting phase or acceleration phase, I will move. Here is not very sensible. As long as I don't exceed, or yeah, overcome this d0, this minus d0, this d0 plus this direction, minus d0, this direction, I will not move. No? The resulting force of the balance must be outside of this to move. And where I am inside, for instance, in the braking phase, I will stop. I will not have an asymptotically behavior in the sense asymptotically, probably we can say, but we achieve the goal. We will stop, better to say, infinite time. Give me 50 minutes to trigger T. I don't know if I have time to upload the material, but believe me, I will upload at the end of the lecture today, so we can update everything. I hope that was not boring. We come back, I show you the mathematical implementation we already seen in different system. This does not take much time. Then we implement. This we upload, and then to conclude, I flesh out a little bit this segue, which is I cannot say it's in a part of the system. Here is a little bit different, but we have some possible analogies. But the system is extremely complex, believe me. But anyway, for the examination, I don't ask. I can ask, but in any case, I give you the model which I presented today. Basically, as I told you at the beginning, the difficulties is not the number of equations, the strata of equation, but what I ask about the equations. Believe me, this is always the principle. If I have many equations, but I ask just the superficial aspect or to implement something which is that is not not the number of equations which determines the difficulties, but the question itself. Okay, don't worry about the questions because I will ask what we did together, and this means you can download the material, and then we can, in particular the software, we can modify and we can extend a little bit to answer the question. Give me 50 minutes, 5 past 3, we will come back to go ahead with this, let me say, summary, but not only summary, related to Lyapunov sliding we will see now, which is the Lyapunov-based approach. We will see in 15 minutes. Okay. Let me close the door. Let me coming back to the lecture. In this sense, let me switch on the lateral camera. Now, second theory. We have seen that one equilibrium point is asymptotically stable. We discussed a lot about that. And another one is unstable. This does not mean that is not possible to control. Again, these are not this unstable equilibrium point. Okay, this equilibrium point is the vertical one. Of course, it is possible to control, at least theoretically. At least theoretically. In some situation, it could happen that we are not able to stabilize a non-equilibrium point. But in this case, we find in a control law this stabilize this. In general, I cannot say because when we are working with a nonlinear system, but I would like to assume that in general we can do. Therefore, I told you I can control the system, for instance, in every point of its, let me say, state domain. Alpha 1 and alpha 2. This position is interesting, nevertheless, whatever the position. We will see now with MATLAB 2. Let me consider this pseudo segue is not a segue because here is not moving. Here is not moving. Not only, this point here is actuated. We have an actuator here in order to control this pendulum in the position pi and velocity 0, exactly at the unstable equilibrium point. This two, or that these characteristics, alpha 1 pi and alpha 2 0, characterize the unstable equilibrium point, pi 0. Do you remember? Of course, to control here, at this point here, we need an actuation, an actuator. It's not exactly the case of the segue. No? I'll show you the segue later. Let me show you shortly what we can do. And it's basically, we know from the lecture which I did, which I held until now. Look, a candidate Lyapunov function. Candidate means if this function here can satisfy all our criteria. Do you remember? Criteria 1 is the positiveness of this function. We have it. Together with the equilibrium point 0, we have it. Alpha 2 0, alpha 1 pi is 0. And the second equation, the second conditions, the derivative in around the equilibrium point must be negative. This is the constructive one, because using this equation, a condition, better to say, is not an equation, it's an inequality. No? We can build the control law which guarantees around the point this negativeness of the derivative, which guarantees, do you remember, that the system is passive, with the system is asymptotically stable at the point, in this case at the equilibrium point, but can be done the same consideration in a trajectory. What is the meaning of the trajectory? I'll show you in 1 second. And the other condition is at the point, the derivative of the Lyapunov candidate must be 0. If all these, let me say, 4 conditions or 2 conditions with the 2 subconditions are satisfied, the candidate Lyapunov function becomes a Lyapunov function. That is just the way to say, just a nomenclature candidate, and then at the end, if we find that this candidate satisfies all these conditions, is a Lyapunov function. Around the trajectory, you can see something like that. If this is the excuse me, the pendulum, I can consider desired oscillations, or desired oscillation, or desired oscillations depends. Around this is minus pi divided 2 or pi divided 2. I can put in trajectory is. Remember, we have seen this as a desired equilibrium set point. The trajectory is in a set of points. Okay, let me do the calculations, which are in this case extremely easy, but conceptually, the calculation of the Kalman filter, excuse me, of the Lyapunov, let me say, approach typically is not so difficult. Lyapunov function candidate, K positive. I will discuss later the meaning of K. I already told you, I think, last time, the meaning of K. Is positive? Yes. As I told you, at the equilibrium point, 0 is 0. Okay. We see that for construction, the first conditions are satisfied. At point pi 0, pi is the position alpha 1, pi, this means 0, velocity, second component 0, in accordance to this nomenclature, to this order, alpha 2 equals 0 is 0. Now I have to find the control law, in this case is the torque, which must be generated by an actuator. No? At this moment, I didn't consider the actuator. If I consider the actuator, it's really a complex project, could be a master thesis, believe me. Around the point alpha 1 pi and alpha 2 2. Should guarantee this negativeness, this t, and at point 0, equilibrium point x0, in our case is pi 0, the derivative must be 0. This typically is guaranteed by construction. Let me show you. Page number 6. Easier, easier. I use this in another nomenclature, but we know not this S. S is exactly this expression here because nevertheless sometimes, let me say this is useful to compact nomenclature. Just a second. Okay. This is S, the derivative of this expression with respect to time is this one. We can see that the derivative at the equilibrium point is 0 because this is 0. As I told you, this condition here typically is guaranteed by construction of the Lyapunov function candidate. This means it is enough now to find the T of D and a control law, which must be guaranteed by the controller through the actuator. The actuator at this moment, no dynamics. This means what the controller does is exactly what the actuator reflects. Let me say one-to-one in order to understand, without delay, phase delay, without any variations in between, as if we have an ideal actuator. The ideal actuator is an actuator that realizes exactly at the same time the control law which came from the controller. The controller is an algorithm which is inside the microcontroller, but of course to realize the controller, to realize the output of the controller, we need an actuator, and to drive the actuator, we need an electric part, we need a converter, we need anyway. I am not expert in this electronic component because here we have a different competence in the lab, or the colleagues that know better than me electronics or power electronics. But anyway, a little bit I have an idea, no? Because as I told you, I came from industry, even though I had a different task, control task. Control means algorithm controller to generate. 1 second. Mm, S of t. Now, one divided, we can understand the meaning of two, as I told you, just to simplify. No meaning. I mean, historically, well, historically, it's suitable, it's comfortable, this simplification, but without 1 divided 2, the results are exactly the same. because I have to I have to judge about the sign of this derivative. A factor 2 does not influence the sign. Instead of S dot, I will do the derivative of this. Hmm? The derivative of this expression is this expression here because the derivative of pi is 0. Yeah. I basically uh, instead of alpha 1 dot, I put alpha 2. We can see. Why k must be positive? And we can see now, because otherwise I have here, if it's not positive, an unstable dynamics. K must be positive, because otherwise I have an unstable dynamics for the derivative of V around, this is not zero, no? Around, the point is not zero yet. Zero is exactly at the point. This analysis, the derivative, must be less than zero around the point. At the point zero, but before reaching the point, I have to go through around the point. This means K must be positive. We can see, we can justify directly from here. Why that? Now we know that the derivative of alpha 2, this is a part of the model. No? If you go back to the lecture, we can see that is the second equation. I can plug in here, instead of alpha 2 dot, I have this long, let me say, expression. Now, I don't know if you remember, is always the same technique, at least using this technique is not the unique one. We have a cancellation term or the terms. You remember, I try to put to zero, to impose zero, this expression here, using a suitable t is easy. This to zero, I can calculate t, which guarantees the zero. This is not enough because it must be negative, and then I will add this element here. Is the idea is always the same. We have seen 2 or 3 times. With this element here, we'll obtain this solution or this final condition. About SGN, I don't have to tell you more because, yeah, we know already. Here, I already clarify why K must be positive. Otherwise, I'll never achieve pi 0. Mm. The dynamics of alpha 2 must be asymptotically stable. This means K larger than 0. Here, the explanation of SGN you don't need. Also, the robustness we discussed a lot last time. We can see here cancellation error, a disturbance. Is this enough of eta larger than this? You remember this? I don't need to explain because the idea is always the same. No? Last time I told you also much more. But in the slide which I upload, you can find exactly the analysis of last time. I put in evidence eta must be positive. No? Do you remember? I forgot to say, but it's written. I didn't clarify again because we know it is exactly what we have seen many times. And then here the analysis of the robustness, which we can see independently of the sign of delta on D, of course, limited delta and limited D, we will obtain in all possible configurations that V dot is less than 0. If eta is large enough, this is the condition. And K positive, no? And K positive. Here again, we have the concept of to approximate SGN. I told you last time. This is the same. This means I don't have to tell you anything about that. Let me see if I can add some different considerations. Otherwise, the idea is to simulate. Let me see. Yeah, this we know everything. Now we can approximate the SGN. I think I already told you a lot of things. We can see probably another thing. I told you K must be positive, but what happens for large and large eta? We know that this means we switch between large and larger upper and lower bound. Sometimes we need, in order to obtain the robustness, or to guarantee, let me say, we can speak about unsensitivity. Mathematically, on the surface, uh, we are unsensible. Um, yes, because the disturbance mathematically is totally rejected. Robustness means is not totally rejected, but we can survive with this effect of the disturbance. Practically is robust. We speak about robustness, but mathematically is unsensible. Um, the meaning of K is clear. Excuse me, eta is clear. Of course, we pay the price. No? To switch between two large values is more complicated, more expensive. We need the actuator with a very high dynamics. Which actuator? The electrical actuator, which is here, which should guarantee this T of T, this torque. For the controller, no problems. It's an algorithm, it's a signal. What the meaning about K? How large should be K? We can optimize also eta, of course. It is a little bit more complicated to discuss, but we can optimize also eta, of course. I don't want to speak uh, about that because it's really complicated. We can also optimate K, but I would like to discuss, this is optimal control in this sense. I would like to discuss, in any case, the effect of K. But we can see from here, as the effect of eta. Effect of eta, we pretend much more from the controller. The output is amplified, we can see here, but also amplified by K. Basically, eta and K are both parameters that must be positive, large enough, let me say, to obtain faster dynamics, in this case, to obtain also the robustness. Here, to obtain fast dynamics, we have seen that v dot depends of k. Large k is more negative, more negative. I don't know if you remember, I told you means is going to v equals 0 faster, but we pay this with larger t also here. This means basically uh, chattering in both cases. Remember the problem of the chattering. Okay, I think I told you everything. Let me now open the simulations. Let me start with the simulation. Let me start with the simulation. I am trying to open MATLAB. No? I am opening MATLAB. Just a second. Let me switch before here so you can see me. Oh, I opened twice. When I open twice, you have to be careful because the system will be extremely slow and it is suitable to close one. Let me close one of the two programs because this is not suitable. Sometimes it happens that I open twice because the beginning I don't see the reaction. Okay, let me share MATLAB. Okay, I think you see MATLAB now. Let me go into the right folder. 1 second. Excuse me. Okay. I have to look for the right folder. 1 second. Why I don't see? Uh, not able to see. Of course, it's not there clearly. 1 second. I will put the memory stick. Mm. Okay, let me put here. One second, because I don't find. Why not here? Oh, where is now the material should be here. Ah, okay, I found it. Mm, okay, look this. I will upload at the end of the lecture all material of today. Let me um, run this program here. This program, this file with the data. No? We can see here data for inverse pendulum. Clear. We know what is m 1 kilogram. The length 10 up to -3 meter. This is a little bit too short. This is 30 centimeter, right? No. So this is too, this is, yeah, 30 centimeter, yeah, right? Yeah, this is better, no? Probably we checked, yeah, yeah, this is 30 centimeter. If I'm not good in this. So exactly. Let me, because when a student in another context asked me about the uh, period of the oscillation. Therefore, we change a little bit in order to put in evidence of what changes. But this is a little bit more plausible. No? We can consider half meter, no? 5 in this case. Gravitational acceleration. We know this uh, friction. Also, how we test it without friction. Yeah, this is really small, but anyway, in any case, not zero, no? Not zero. It could be, this could be, it's not totally, but typically we have a larger value. It depends on the friction on the joint. What is I intend? Let me show you what I intend. The friction of the air depends on the air, but this is, you can understand, is not so much. But if you consider, typically the friction is not negligible, because this joint here, we have, and this point here is connected with the rotor of the actuator. No? This means this could represent as a problem. No? The air, of course, could be also zero if I consider vacuum, no? But this is not the case. But of course, here we have a friction, we have also a static friction. The problem is, you can understand me, if we want to analyze in detail, yeah, could be extremely complicated. K positive 10, eta larger, just to check. Again, this K and theta, I worked also in optimization, this K and theta. Isn't so a topic. Could be nice if you want to work with me in the thesis, to attack also for a relatively, let me say, easy system, the optimization of these two parameters. Okay, let me, no, excuse me, I made a little bit mistake with MATLAB, no? Ah, excuse me for, again, here, B, I don't know now, probably I lost the orientation, what I told you uh, with Zoom. Again, here, the friction here could be also relevant, no? Not only 0, comma. because here this joint here is characterized by the motor. This point here is connected with the rotor of the motor. Could be really to be analyzed this friction here. In particular, we have nevertheless let me say yeah, static friction. Think about um, the rest moment of a motor. Look in YouTube, no? Or the rest torque, no? Rest. This should be overcome in order to start. And of course, when we are in the braking phase, we will stop also because of this rest moment, because isn't the friction, static friction, the sets we can imagine. Okay, k equal 10, eta equal, it doesn't matter which one, relative large, could be also optimized. If you want, we can think about a possible master thesis. Why not? Or in general thesis. Okay, let me now open the file, pendulum, we can see here. Let me click. I am waiting for. Let me share now Simulink. Yeah, I think you can see Simulink now. Look, an inverse pendulum, it seems to be so complicated. It is. Therefore, if I try in this kind of lecture to show you the same way, now I show you the equations, nevertheless. Let me don't consider this error here. This is an error, a disturbance. D of t is an error, a disturbance, exactly. What we have here at this level here is exactly. I hope that you can see Simulink. Let me see. Yeah, is exactly the model. No? Position, angular velocity, angular acceleration. What we have here is basically the feedback of the component of the gravitational torque. We can see, you remember, G divided L, because of the simplification, multiplies sine of alpha 1. This is alpha 1, the position, the angular position of the pendulum. Here we have the friction component. Look, I put also here a possible static friction, in which we have the coefficient 10 as a possible coefficient of the static friction. Of course, I have to divide SB by M by inertia, ML squared. If you want, I show you later what changed the simulation, even though this part here is not considered in the model. In the model to realize the sliding. What we have here, this part here, is the inertia, as before, which divided T. This is the torque, which in our case came directly from the controller without considering any signal conditioning, digital continuous converter, the actuator model is not there. This is also another interesting topic. I will start in any case today when I conclude with this uh, discretization, discretization of a model. In this case, the discretization is related to the control law because the system remains continuous, the physical system. But to design uh, the control law, which will be realized in discrete form in a microcontroller, we have to do some consideration. I will tell you today. What we have here, this system, this blocks here, is exactly the control law. Let me analyze a little bit together. The control law consists of many elements. Look at this, for instance. You remember the equivalent part, remember we called equivalent part the part dedicated to the cancellation, and the switching part. We can see here the switching part in which some student ask me what happens if I increase eta. Theoretically, I have to increase eta in the M file here to be a little bit faster. I increase directly here. But let me reconsider the original form. Then I approximated the sign with hyperbolic tangent. This 5000 is this gamma. Do you remember I told you about this gamma to approximate the argument of the hyperbolic tangent? The argument of hyperbolic tangent is gamma, relatively large to approximate the function sine. Of course, also this could be optimized. Could be a topic of our master thesis. The argument is gamma 1000 multiply s of t. What is s of t in our case? It's easy. We have, look, alpha 2. You remember here we have alpha 2, the velocity, minus 0, which I didn't put, plus k. Also here some student ask me what happens for large k. Instead of change k in the let me say in the M file, I change directly here. But let me start with the original case. K, which multiply what? Alpha 1 minus pi. Do you remember? Because we want to stabilize, we want to control at pi with velocity 0 for each disturbance, for each cancellation error. The rest is basically the elements of the equivalent part, which are dedicated to the cancellation. Let me start with the simulation. Okay, let me show you what happens. Basically, starting from an initial value of pi divided 2, I will show you why is pi divided 2. I will going to pi 3,14 and so on. We can we can prolong the simulation here. We have just 0,5 second, half second. We can also at the beginning test this with some disturbance. We can see here slowly, not so slowly, in half second from this situation here, pi divided 2 or the minus pi divided 2 is going in half second in this position. 3,14 is our pi. No? Why I'm starting from this position, pi divided 2 or the minus pi divided 2 really should be in this form. No? And according with our yeah, representation, pi divided 2 is this. No difference because it's the, where is this pi divided 2? I put the more difficult situation. Look at here. More difficult situation means that alpha 1 the position pi divided 2 because I have to overcome, you can see here, no? We have to overcome the maximal, the maximal, the maximal gravitational torque of the moment. You can see here. Why alpha 1 at pi divided 2 with velocity 0. Of course, if you have a velocity negative, it's more difficult too. How we can realize the difficulty? Looking at t. Looking at t. Let me show you. Here is clear, no? What I did. We have this position here, I am going here. But of course, if I have in this position with negative velocity, this means we have a negative, let me say, down and clockwise. Of course, it's more difficult. Let me show what is the meaning of difficult. Why am I speaking about difficult? Is here, t. I don't know if you see. Here we have a t. You can see I started from 100. And of course, why this? Because I'm switching. Huh? Let me put as negative velocity. Keep in mind this. No? Keep in mind this a little bit. If I go here and I put an initial velocity not 0, this moment let me share. At this moment is 0. Let me exaggerate. Minus 10 radians per second. This is the unit which we are using. Of course, we are waiting a little bit more effort. I don't know. I think it should be also already visible. Because I am in this position and the trend to go, let me say, down, but our desire to stabilize this point here. And then we introduce disturbance. I don't know if I share. A little bit tired there. It's yes, it's relatively difficult to see the differences. But a little bit. Because I don't know if you remember, we reached the surfaces earlier. Let me redo. Here we reach the surface. The surfaces means the point in which I switched. Remember, I told you about that. We achieve the surface around 0,03. The point in which I start to switch, chattering. Let me redo again the simulation with, I don't share, but what I am doing, let me go. Let me remain here for you. I go inside without, I think it is, no, this is the, uh, So we can see also from here. This is what is this? Is the position? No, I don't know what is. 1 second, because I mix everything. Ah, excuse me, I have many windows to hold the lecture per Zoom with MATLAB is really challenging. Okay, this is the picture which I told you. I reached at a little bit earlier than 0,03. Let me share. At a little bit earlier than 0,03. Let me, now I didn't share, but believe me, I coming back at the initial condition for the velocity 0. Okay, let me see what happens. Yeah, we can see it seems to be that I achieve a little bit earlier. Yeah, 0,02. Meaning, the meaning, the meaning is, 1 second, I'm totally, yeah, that I will achieve the initial conditions, excuse me, how possible to say, the surface earlier. This means I can reject disturbance earlier. Look, here is when I achieve, here is exactly the dynamics of S of t. S of t is going to 0, and I will achieve 0 earlier if we don't have velocity negative. Let me say more or less here at time 0,015. Please remain here, because you remember the first goal is to achieve S equals 0 as soon as possible. Now let me, without sharing, showing you what happens with the negative initial values. We can see that instead of 0,015, we have here 0,02 A2. This means we lose a little bit time to reach the surface. Try to do at home, of course, what happens increasing eta, we will obtain faster dynamics. And let me do the last very important consideration, considering a disturbance directly in output. This means we have somehow something which disturbs the position. Of course, this is not so extremely realistic, but can be considered. Typically, we have a disturbance here at the torque level. But in any case, if I am able to overcome this disturbance here, this means I have to consider larger, this is really extremely 20 centimeters, so 20 degrees, I think this is radians. This is radians. 20 radians is extremely, therefore we increased a lot eta. Eta must be a relative large. Now, let me consider something more realistic. Instead of 20 radians, 1 radians. Otherwise, I have to increase eta, and therefore the I value at the beginning. You can see that independently of the disturbance directly in output, we can see at the beginning the control law have some difficulties. Why that? Because also this is in a delay in order to achieve the s equals 0. When we are at s equals 0, theoretically, we are unsensible. Let me see if I can show you s of t. But anyway, I would like to go ahead. You can look at that basically we achieve a little bit later. Huh? Let me conclude showing you a few things about, but we can see that we obtained the goal, of course, at the beginning. As long as I didn't achieve, probably the switching, I have it somewhere. But anyway, I don't find now quickly. Let me conclude because I dedicated a lot of time here, which is okay because it's interesting, but I would like to start also with the discrete today. Let me sketch a little bit an interesting application. This is not included in the exam, or if I include, the meaning is to give you exactly the equations and to ask something, but extremely easy. Same way, look at these two equations. It's not the goal to clarify the meaning of this. It's the physics. Eventually, I will give you these two equations, but I would like to tell you very quickly the idea. Assuming that I want to control the system at pi, again, pi 0, pi 0, pi 0, pi 0, and x1 equals 0, x2 equals 0. What is x1 and x2? If you look at these equations here, we have again as before, a little bit more complex than the model, alpha 1 and alpha 2, if you remember. But we have also here, because of the movement uh, of the car, let me say. Let me show you in a picture in order to understand better, because very important to focalize what I am doing. One second. Look at the picture a little bit. It could be useful to. 1 second. Why I don't find now this presentation. Okay, probably this. Let me share. Did you see this one? Of course, it's again, it doesn't matter in which position. I mean, if this is the reference position, again, I would like to control in pi, S in the lecture. But we can see the car, and the equations are quite complicated, I would like to say. So I don't have time to explain. But anyway, I gave you eventually. even though I don't think that I will tell you about that, but it could be nevertheless. I don't think that I will give you this exam. But anyway, we have x1 and x2, position of the car and velocity of the car. Look at this position of the car and velocity of the car, plus, let me say plus, angular position of the arm and its angular velocity. Look at this possible Lyapunov candidate, Lyapunov function candidate. This means I would like to stabilize in one point, 0, 0, the original point, and at the point alpha 1 pi and alpha 2 0. This is the goal. 1 second. Oh, very. No. I can stop. Stop in 10 minutes. Come okay. Ich mache eine Pause. Okay. 10 minutes. Yeah. But what happens if I do this kind of controller? Let me come back. This means that I try to stabilize at pi in vertical position, but I can't to stabilize in the meantime, or the equilibrium point which I want is the arm at the position pi 0 and the car in the original point, if 0 is the original point, of course. What is the meaning of this practically? The meaning is if I have a disturbance or if I push ahead the arm, the system try to work against, because the equilibrium point is pi 0 and the original position. This means if I do this kind of, if I design this kind of control, I can do, but I cannot run. The policeman putting ahead the arm will not run. We can do nevertheless. I'm a little bit tired. At 10 minutes now, we will take a rest a little bit, and then we will start with the discrete. 1 second, because I'm totally confused. Okay, here. If I start with this Lyapunov function candidate, I will put, you remember, x1 derivative equal x2, x2 derivative equal the equation alpha 1 derivative alpha 2, and the second long equation, a little bit different as I told you before, but anyway, we can see some elements a little bit similar. Doing the calculation, in order to calculate f, I do v dot, as I told you before, it's extremely complicated, not complicated but boring. I will obtain an f which stabilizes also x1 equals 0, x2 equals 0. But in the same way, we don't want this. But we can do. The same way, typically, we are using an Lyapunov function like, in which I don't consider all states, but I will consider just as before alpha 1 pi and alpha 2 0. I don't have any specification about x1 and x2. This means no consideration about x1 and x2, can be everything. If I do these calculations, believe me, considering this, I will obtain, let me say, not similar as before, but in any case, we can calculate f of t in a similar way with some approximations and so on. What is the meaning of this design? I neglected x1 and x2. This means the idea is to stabilize. Did you see me? Yeah. The idea is to stabilize just this position. I mean, if I give a disturbance, the car will move to stabilize this. But if the policeman push ahead the arm, the car will move ahead because he tried to stabilize this position. This means the policeman or the driver, in order to run, in order to use this system as an yeah, moving system, maintain the position, and the car will run. Of course, because of the friction, because of the losses, we will have an equilibrium. This means the car will not, the control system will not will not able to repristinate the position because the driver will maintain, and we will after the transit we will travel with a constant velocity as long as the acceleration, let me say the force, the horizontal force F is the force of which guarantees the movement generated by the actuator of the car, which is in the wheel. Of course, this is a little bit more complicated to technically, but conceptually it's clear. No? The actuated elements are the wheels of the car, which try to guarantee, thanks to this, let me say, Lyapunov-like, because we didn't consider any element x1 and x2 of the car. The force we can see here is the horizontal force, which is generated by the actuator on the wheels. This means we can calculate with the second Lyapunov function, which is not exactly Lyapunov function because the function does not contain all states. If we neglected x1 and x2, this means we'll try to stabilize this equilibrium point independent of x1 and x2. This means could be every value. And in particular, practically, we will run far away from the original. Let me take a rest before starting with the new topics. Again, here I calculated the force which must be guaranteed by the actuator on the wheels. This is the force calculated, which is somehow in the controller and must be guaranteed by the actuators. I did some simplification, the calculation, but it's not, again, I will never ask about such kind of system in the exam. Let me take 10 minutes, 15 minutes, then we will come back and we will start with a new topic, discretization, because I already introduced a little bit some ideas, what is the meaning and so on. But the goal is to open at the end the new topic is very important in a selected topic. Again, is the model predictive control, which is basically in the form, in the applied form, is in the discrete method, discrete control method. And this is extremely important in automation, robotics, and so on. Anyway, the example of today, so at least we have seen how this selective methods problems can be applied also in some robotics project. Let me say, this is not an exercise for the exam, of course, because this is really an extremely difficult project. We have here 3 experimental setups, one more static here, and 2 really as the policeman. We both to travel here in the lab. We will see in 15 minutes, let me say, half past. So we do we start with the discrete. And this is let me say, the last topic. I have seen that the last lecture is in the 9th, I think. The 9th June. This means we have basically 3 lectures. And this is enough to introduce the discrete system and to tell you about the discrete. It could be that I have a little bit also more time for another topic, but let me start with this, then we will see. See you in 50 minutes, half past. Thank you for your attention. Let me drink again a little bit something in order to conclude the lecture with my voice. Okay, let me restart now with a new topic. The goal is at the end to present the model predictive control, at least in its fundamental, in this fundamental structure, or let me say the inspiring idea, no? Inspiration idea. Even though in general MPC is an optimization control strategies. In this sense, in general, if the problem is not convex, I will tell you about what is the meaning of convex and so on. We need to use solvers, or at least a solver. I don't have time really to tell you about the solvers here. Very often, in case of not convex optimization problems, we use a particle swarm optimization methods. It could be that I can tell you about that. It could be at the end as in a seminar form. Typically, I don't do because this is more a topic for projects. Because in non-convex optimization problem, we have to really to be able to program. You are able to program, but in our form of examination, yeah, this is really something more suitable for thesis in this sense. Okay, let me now start with some issues in discrete systems. I think we have 3 lectures. This means I will dedicate also next lecture to this topic. And then I think I will start with MPC. Yeah, but in any case, we have time. Okay, let me, in this half hour, 20 minutes, to introduce the discretization. And of course, we will see, we have a time to analyze in depth, excuse me, or the deeply, just the linear system, but linear systems. But I will tell you a little bit the idea in discrete, just flesh out. In the exam, I will ask you just about the linear system and so on. Emulation methods. We can see here that the key idea is to build or to introduce, better to say, the analogy between numerical integration and differential equations. I don't have time to go in depth on this, but nevertheless, we have a modeling continuous. We have seen until now modeling continuous, and basically we can nevertheless discretize. We can discretize the model to obtain the discretization I will tell you, and to obtain a model which is discrete. Now, this could be in done in any time, and we will see that we will introduce an interesting operator, no? This Z operator, which basically represent somehow a shift operator, which can help to build this analogy between, let me say, Laplace transform. I didn't tell you about the Laplace transform. I will tell you a little bit now, probably you know from different courses, and the zeta transform, in which zeta is an extremely complicated variable, but I try to introduce it in a really easy form. Yeah, the basic idea of this emulations method. Basic idea is once we obtained And a good controller, do you remember this at the beginning of the semester? We obtain a PI controller, we can see here, in time. No? We have a good controller, a PI controller, which works very well in continuous, which works very well in continuous. The idea is to discretize this PI controller using, again, some methods, using somehow this Z or the shift operator in order uh, to check, to validate if also, let me say, the corresponding, the discretized controller maintains the performances which we tested, which we validate in continuous. This means this emulation system, emulation, the name is in a Latin word, this means somehow similar. We do everything in continuous as we learned at the beginning of the semester. Do you remember this method in a linear system with the place of the eigenvalue of the eigenvalue of the matrix and so on? But anyway, it doesn't matter which method you used. You have this, which guarantees in continuous some performances. Please pay attention. The system or the systems which we are considering in this course or the technical systems are continuous systems. This means the emulation method makes sense in which form we realize the specification or we achieve the goal using continuous controller, which we are able to design, and then we discretize just the controller directly, let me say. I don't want to use the direct word because the direct is used for another method. We emulate, let me say, in discrete form, what we obtain in continuous. What we obtain in continuous. We will see that in the MPC we use another method. But anyway, I would like to tell you about this method because also this can be used very often. This can be used very often. Not directly for MPC, but for PI, for instance, for PID. And this is important because I started the course using using in the sense introducing this state space controller PID, which is in this form, I think is selected because probably you didn't see in the course. Typically, in continuous, we are working with Laplace. No? We are working with Laplace. Okay, here is the form of our PI control in which the KI control parameter is KP divided TI in this form here, but this is depends of the books, depends of the literature. No? KP is exactly KP for the proportional part, and do you remember until now we have seen KI for the integral coefficient in this form is KP divided T. No? But we have two parameters to be set, KP and TI, in this form here. If you consider KP divides TI, of course, it's just KP and KI, as you want. About that, I already told you. Let me see if I am... And probably this sentence here could be commented a little bit better. When we realize the controller, in this case, I consider the PI, but you can consider also PID, everything which we have seen. You remember, we have seen integral combined with the state space controller. I don't know if you remember. Everything which we have, we can realize in discrete. Once we have the realization, we will see with different approach. I think we will see just one approach because I don't have time. Anyway, once we have, let look at the sentence here. After the discretization, we hope, this is important, this important sentence, that the property of our original continuous controlled system that uses the continuous controller are preserved or guaranteed. Preserve is very strong. Anyway, more or less, we can use, despite, please pay attention this word, the approximation. Why that? Because the discrete or the discretization of a differential equation, or an equation of a signal, the discretization is always an approximation. Exactly. Exactly. Again, I can read. Hope means that we do our best to maintain these characteristics, or these properties. This means stability in any case, dynamics, robustness, and so on. This word we know. Again, this is the PI, just an example. I do the Laplace transform. Now, it is nice. Of course, we can do also the same analysis in time using matrices. Of course, I can do. But the idea is to use also Laplace, because probably you know, and this, in my opinion, is a little bit rapid. But if you look at the first part of the lecture, of the course, in the lecture of the first part, you can build a law, and eventually also you can redo this analysis, everything in term of matrix. But let me go ahead. Nevertheless, we have an advantage here with Laplace, that we can build an analogy a little bit between zeta transform and Laplace transform. And this, in any case, could be useful also for your education in the sense. This is the model in Laplace. Let me now introduce somehow the Euler formula rules. This can be used also for discretization of nonlinear systems. But let me apply now to this PI controller. Look at this. What is the critical elements in any PI controller? Critical in the sense, the most important, I already told you, is the integral. Is the integral. You remember, for different reasons. This means to approximate this equation here in time. Of course, the critical element is this one, because this is a static, let me say, element. I will clarify later. Let me approximate this. Do you remember the concept of the state, which I associated to the I part of the control, integral part of the control? Do you remember xi of t I called xi of t? Now, our time becomes k multiply t, in which t capitalized. You remember, t not capitalized, our time becomes, in this approach, k multiply t capitalized, in which k is in a counter starting from 0, which corresponds to t equals 0, t not capitalized, and then 1, 2, 3. It's an, let me say, it's a natural number. And sometimes you can find the literature instead of kn. T is an important concept because it's the sample time. In order to show you what I intend, I don't know if I'm in a better picture here. I have it. Look at this picture. This is the situation. Using Euler forward, we will see the difference very shortly, because the course is not dedicated to the discrete system, but selected problems. The problem is we will see this model predictive control, the control of robots or systems in general using model predictive control, which is a discrete technique. But in order to understand a little bit better, I would like to introduce, probably you know already, but anyway, I am sure that not all students know exactly what I intend for a discrete system, or in this case, discrete signal. I would like to distinguish in between. Yeah, we can see in a continuous signal over time, continuous time here, represented using an Euler forward. I will clarify a little bit better next time the notation. But we can see that we don't have a continuous signal, but we have a stepwise continuous in accordance of T capitalized. Sometimes also here in this slide, I use TS, simple time. Excuse me if I use different notations, but also for you, I hope it's a good idea to be flexible with different notations because each book uses its proper notation. This means sometimes it's T, sometimes TS. S represents sample, no? T is the time, the interval of time. This in complicated situation could be also variable. No? This means, anyway, not necessarily fixed. This means a continuous signal becomes a stepwise continuous. Now, let me come back a few minutes and then next week we will restart from here a little bit. Look at this. Do you remember the concept of the memory is summarized here? It's a book we call Q, no? Which is the integral starting from 0 up to kt of the error. Look here. This representation is the discretization, not exactly discretization. I discretize just the time of this integral here. Instead of 0, I have 0. Instead of t, as I told you, I have a k multiply t. As I told you, t, not capitalized, is replaced by k, continuous, excuse me, natural number, multiply t, which is given. Please pay attention, this t could be also variable, but this is a little bit more complicated. Let me fix it. Of the error. You remember, mathematics, we have to distinguish this argument with respect to this variable here, even though this represents the time, this represents the times, but this is the time inside the integral. This is the time of the extreme of the integral. Huh? Now, what happens from here to here? From here to here, I am considering exactly that when I consider discretization of this function here, we have a stepwise continuous and not a continuous anymore. This means this representation here, using the discretization, becomes this because now this function here, this function which is not continuous anymore, yeah, this function here because of the discretization, this function here in this position here with respect to this is not continuous anymore, is stepwise continuous. This means the integral here, even though we have a kt, but this is a value, it's still continuous. If I want, let me say, realizing discretization of this internal part, now I have to, with respect to this, I have to consider this is an approximation. We have seen also in the picture as before. If you remember in high school or in math, if the integral represents the surface, let me say, between the function and the x-axis of this horizontal axis, we have an approximation of the surface. If I consider this discretization, it doesn't matter which kind of discretization. In this case, Euler forward, but any kind of discretization realizes an approximation. Let me explain a little bit better what I intend. Look, sometimes, no, as I told you, TS, often indicated with TS in the literature, sometimes also I used, depends. Inspiration, which book inspired me? Why this representation? And then we will conclude. Recall this, no? Xi is the new augmented or the pseudo state, because it's in internal on the numerical control. Okay, error instead of yes, the counter is I, no? Yeah, the counter is I. Basically, in this sense, K is somehow fixed. No? We have the values. We can fix K. We are used in another counter. This T that we had here basically is here. Why that? Because if you see again, I multiply T can be interpreted directly from here. We can see AIT, if you like, AIT at this position here, at this level here, no? Which is multiplied by T in order to get the surface. No? This multiply T, I will get the surface. Now, the counter here of the sum, the counter, the counter is I starting from 0 up to K minus 1. The reason is exactly here, because if you look here at, excuse me, at this time, we are considering, let me say, the last surface. This means I have to run, let me say, until this point here, which is K minus 1 respect to here, no? Or is K, and this is K plus 1. Therefore, I am running not until the end of the interval, but the interval before. Because this point here, which is respect to this, is the previous step. I mean, I can write here K minus 1, which multiply T, everything K minus 1 in parentheses, which multiply T. I can write K multiply T. This means to integrate until K multiply T, K multiply T, I have to consider in its approximation the sum until K minus 1. It's a little bit confused in the representation, but it's the representation which you can find also in books. Now, I am concluding for today. Let me show you now what we can do for the PI. Here we don't need to do anything because T is equal K multiply T. I already told you. Here we have this, we don't need to do anything, but Q of KT is our new state, or the augmented state, which basically can be represented in this form. Why that? This form states the dynamics of the system. The integral, do you remember, is the storage effect. This means here must be considered this storage effect. Q at time, let me say k plus 1, everything multiplied by t. I can put in evidence here t, no? I can put in evidence here t. Basically, the step after k equals the step of k, q is the state, no? For the state, plus the new contribution, a new area. Again, this is the past area. This is the new one. If you look at the picture, we can understand intuitively without many words. The area at this point here, which is kt plus t, or if you want, parenthesis k plus 1, parenthesis multiply t, this area is this area here, the past, plus this element multiply this. The past plus this element, the amplitude multiplied the interval. These two equations characterize the PI integral. Very important, the Q, which is the augmented in discrete, which basically states the memory, state the storage effect. Because what we have at time kt plus t, what we have at time kt times t in terms of surface is, let me say, the past surface, the blue surface, this here, plus, excuse me, this here, plus this element here with the amplitude multiply t. The amplitude at time kt multiply t. And this can again justify why the integral here is running until k minus 1. Think about that, but it's intuitive in this sense. This is the discretization of the controller, which for us was okay, let me say so, or guarantees the performance in continuous. But we want to implement in the microcontroller. This means we have to analyze what happens in discrete form. Next week, we will restart from page number 3. I try to accelerate a little bit, but we have a time at least to present the MPC in detail, because in accordance with what I read in the calendar of Huge University, we have 3 lectures. This means no problems. Okay, we did a lot of things also today. Believe me, I will upload. I will send you an email to inform you this material is in the WeCamp, I think is we can say so. And I will upload also this presentation in the YouTube. Very important in any case is also the software, because through the software you can modify it a little bit. You are sure able to answer the question in the exam. Again, the questions also, the software are related what I told you during the lecture. This means you can use the YouTube, you can use all material is there. It's not so difficult to answer the question. Again, 1 people can do in the group, 2 people, also maximal 3 people, 2 students in this sense. More than 3, I didn't have good experience in this sense. I am here for your questions. Please question me. I have time for your questions. But in the meantime, I am closing the lecture. Thank you really for your attention, but I remain here in the room for possible questions. Yeah, I will start nevertheless to upload now the material we can. Thank you to everybody, and question me if I have a question. In any case, I will answer if I am able to answer also.